Have you ever wondered how tires keep cars stable on the road? Why do they allow you to start and stop a car? Let's take a look at some awesome physics and find out. As you may have guessed already, friction is in play. Friction is a force that can be static or dynamic. Static friction resists motion between objects when they are not moving relative to each other. The lack of movement is why we call it static. This is why it can be difficult to push a piece of furniture out of place. The rubber tips underneath it are holding it tightly to the ground. Static friction is what you have to overcome to get it to move. Think about an eraser or a car tire. Friction is necessary to move the wheels out of their place and for the eraser to be able to rub off graphite from paper. On the other hand, dynamic friction is a force that arises due to relative motion. That is, when two objects come into contact while both moving. This can happen when they go past each other, scrape side by side, or roll on one another. The universe tends to be in constant movement. So, in this video, we'll mainly focus on dynamic friction. Friction doesn't only happen between two solid materials. It also happens within gases and liquids. However, in the case of gases or liquids, the molecules are more scattered and come to contact with each other for very brief periods of time. You may have guessed that friction is determined by the surface area in contact between two objects. However, this is not necessarily the case. This is because the molecules at the very edges of two surfaces are not always rubbing against each other, and if they are, they do so at varying levels of intensity. You may be familiar with friction on an intuitive level, but let's figure out what the particles are doing at the levels we don't observe with our naked eye. An interaction between a tire and the road looks very different on a molecular scale. In this case, it's hydrogen, carbon, oxygen, sulfur, and nitrogen, among other molecules, interacting with each other. Molecules can form bonds in various ways. The thing to keep in mind here is that these bonds break and reconstruct as two surfaces come in contact. You can think of this like your Wi-Fi connection. The closer you get to the router, the stronger the connection. The closer the molecules come to each other, the stronger their bonds. For example, when you rub your palms together, the molecules on the surfaces of your palms start to interact with each other with increasing intensity. As your palms move up and down or side to side, the bumps and dips of your skin collide, while the bonds between molecules resist and want to keep the molecules together. We experience this as friction. If you continue rubbing your hands, the molecules continue to interact and transfer energy between them. This increases the overall kinetic energy in the molecules. That is, energy associated with motion and movement. As a result, your palms are heated, and you feel a bit more fuzzy. Is that all? Well, if we dive one level deeper, we can see that when two molecules come into contact with each other, their atoms start interacting in more intricate ways. To measure friction at an atomic scale, scientists have created a device called an atomic force microscope. This device attaches one atom to a spring and drags it across a surface. To better understand how this works, imagine yourself hiking and going up and down a series of mountains across a rocky trail. You are now in a similar position as the atom. This atom has a variable energy potential. That is, how much energy it is capable of exerting. When the atom on the spring is dragged on top of a bump in a surface, it gets a little squished, and so the energy potential increases. In our analogy, this is you climbing to the top of a mountain. On the top, you can relax and restore your energy. Then, when the atom is going down from a bump into a dip, it uses this gained energy, releasing heat. The hotter the atom, the more shaky it becomes, and the higher the chances of it interacting with the surface. This increases the amount of friction. On this scale, it is also important to consider three additional factors: roughness, adhesion, and lubrication. Roughness is the measure of steepness. Adhesion is the measure of stickiness. Lubrication is the measure of slipperiness. In our hike, you can think of this as the steepness of the mountains in the way, the muddiness in the trail, and how wet it is on that day. Each one of these influences the amount of friction the atom experiences. Now that we've covered how friction works between the atoms, you may be wondering what is going on inside the atom itself. However, we run into a problem: the Heisenberg uncertainty principle.
Goddamn right.
The Heisenberg uncertainty principle states that at any point in time, we don't know either the precise position or the precise momentum of a particle. When we measure an electron's position, its momentum becomes hard to tell. On the other hand, if we measure the momentum of the electron, our guess of its position becomes a lot less informed. This leads to a lot of problems in science. Since both momentum and position of electrons are important in thinking about friction, I'm afraid we'll have to talk about this another time. Regardless, we've learned that friction is a force that can be thought of in different ways, depending on how much you zoom into the area of surfaces interacting. Whenever two objects come into contact, you can bet friction is involved.